Every once in a while, STP, which just does a wonderful job of just stopping switching loops before they can even get started, it's going to give us a bit of a kick. And the kick here is that STP is only going to leave one trunk open between any two given switches, even if we have multiple trunks between them. We could have two, we could have six, but only one path is going to be used, and the other five in that case would just be sitting there. We'd really like to use those other available paths and the extra bandwidth. In today's networks, we don't want those paths just sitting there, but we still don't want switching loops, so it's not like we're going to do anything like try to disable STP. Two ways to make this happen are per VLAN load balancing and ether channels. PVST makes the load balancing option possible in the first place. I've mentioned a couple of times, and we've seen it in iOS help a couple of times on the switches, that every VLAN is running its own instance of STP in PVST. Now we're going to see that in action after a brief discussion of why we would use per VLAN spanning tree. Let's say you have 50 VLANs in your production network. Now we know that one switch by default is going to end up being the root for all VLANs. We've hammered that into the ground. We got that. But the reason I mention it again is that we're going to have one root bridge selected, and in our simple little two-switch network, we're going to use this as an example. We'll assume it's the one on the right. We also know that the non-root bridge is going to select one root port, and the other port leading to the root bridge will go into blocking mode, because out of these 4 ports, only one will go into blocking mode. However, if we have 50 VLANs in that network, that means traffic for all 50 VLANs is going to go over one of the 2 available links, and the other one is going to be totally idle. And that's not a good way to run things. That's not an efficient use of our resources. What we can do with per VLAN spanning tree load balancing is fine-tune the port costs on a per VLAN basis. Sounds familiar, something I think we've done before. And what we're going to do is enable one port to be selected as the root port for half of the VLANs and the other port to be selected as the root port for the other half of the VLANs. That's per VLAN load balancing. So here, it's not exactly 50-50 load balancing, because what we would do is something like this. We configure it so our switch here, our non-root, picks this port as its root for VLANs 1 through 25, and then this port for its root for VLANs 26 through 50. So it's not 50-50 load balancing, but it's still better than sending all the traffic over one link and then just leaving the other one idle. Because let's say VLANs 1 through 25 send twice as much traffic as your VLANs 26 through 50 do. Well, then you would have a 66-33 split of the traffic over the links, but that's still better than a 100-0 split of the traffic. So let's see this on the live equipment. And what I've done, I've deleted all the VLANs from previous labs, and I've added VLAN 100. So we're only dealing with VLANs 1 through 100 because the concept is the same whether you have 2 VLANs you're load balancing with or whether you have 50. So here on switch 1, let's go ahead and run show spanning VLAN 100, and we see switch 1 is the root, which is what we expect from previous labs. And switch 1 is the root of VLAN 1, and it's going to be the root for every VLAN we add to our network. So right now, let's go over to switch 2. We'll run show spanning VLAN 100. As we expect, one port is in forwarding. That's our root port. The other one is in blocking mode. And also, as we'd expect, we're going to see the exact same thing with VLAN 1. And no matter how many VLANs we add, we're going to end up seeing the same thing. But let's say that we want the VLAN 100 traffic to go over port 12. We've determined that they're about the same workload, VLAN 1 and VLAN 100. We're going to send the VLAN 1 traffic over the trunk on fast 11 and VLAN 100 traffic on the trunk on port 12. What we do then is mess with the costs a little bit here. And we've done this in another lab, so nothing new here. There's the cost command, and we're going to put a 12 there. Looks like we had some kind of immediate effect, and you can see already the cost change took effect immediately. And here we've got listening mode, so it's already in listening mode. It's already blocked 11. So let's just give that a little bit of time. Now it's in learning mode. And it's going pretty well. We're not in forwarding mode yet. I'll hit the elevator button a little harder. That'll make the elevator arrive quicker, right? There we go. It's in forwarding mode, and you get your line protocol on VLAN 1 is up. So anything else we need to do there? Let's go ahead and make sure everything's okay with VLAN 1, and it looks like the exact same thing happened on VLAN 1. What happened there? Did I do something wrong? Because we wanted the VLAN 1 traffic to stay on trunk 11, so to speak, interface 11. And the reason that happened is I used that spanning tree command that changes the cost for all of the VLANs. If you use spanning cost and follow that with a number, you are changing the cost for every VLAN. But that's not what we want to do for per VLAN load balancing. We just want to change it for VLAN 100. So we need to use a slightly different command. Let's go in here and take that off first off. Just do an up arrow, Control A, bada bing, bada boom, and there you go. Could just use my up arrow there, but you can see already port 12 is blocked again, port 11's back in listening mode, and everything's back where it was. We did this earlier, and I just wanted to do this as a reminder for you that for load balancing, you can't use that spanning cost command because that's changing your port cost for all your VLANs, and that's not what we want to do. Otherwise, we're just taking all the, if we do that, we're taking all the traffic from the trunk on 11 and we're putting it on 12. That's not load balancing, that's just load moving. And we don't want to do that. So let's go ahead and run that command again. Everything's back where it was. Now, let's use the command that only changes the cost for VLAN 100. And it's spanning VLAN and then change the cost. And we'll just change that to 12 just for fun. And we get a quick message there, show spanning VLAN 100. You can see that it has changed the cost for VLAN 100. But if we check 1 right now, whoops, you'll notice that is totally unchanged. So VLAN 1 is not impacted by what we did at all. It's still forwarding on 11, blocking on 12, but now it's learning on 12, so it's going to be in forwarding in a second. This is per VLAN load balancing. It's a fantastic feature. You just have to remember to use the full VLAN command to change that port cost and not change it for all of them. Also, you got to see a great message when I typed a 1 in there or left a 1 in there. If you type this in and you get this message, it really just means that VLAN 11 doesn't exist, because it doesn't. So you will get a message that says spanning tree instance for VLAN 11 doesn't exist because VLAN 11 doesn't exist. And we're now in forwarding mode. So you can see how beautifully this works. So on the same switch, we're forwarding on different ports. For VLAN 100 on switch 2, right now we're blocking on 11, forwarding on 12, but on VLAN 1, we're forwarding on 11, blocking on 12, and that, my friends, is per VLAN load balancing. It is a fantastic little feature. Now, that is a great feature, and the next one we're going to talk about is really good too, because what we can do with ether channels, we're going to logically bundle our physical connections, and we're going to fix that so no matter how many trunks there we have, anywhere from 2 to 8, STP is going to see it as one interface. It's really a great feature. So I will see you in the next video. We'll talk about ether channels for a few minutes and then we'll configure one. See you there.